So welcome back. Our next speaker is Bailin Song, who's another one of Ron's students. He'll be speaking about global sections of the parent complex and Calabi-Yau.
Thank Andy for the introduction, and thank the organizers for invitation. It's my honor to speak at the CMSA. I will talk about the global section of Calabi-Yau complex on compact Calabi-Yau manifold. So my talk will include 3 parts. First, I will introduce the Calabi-Yau complex, and then I will talk about the global sections on Calabi-Yau manifolds. And the third part is the sketch of proof. It will relate to the action of algebra vector field act on beta gamma BC system. Okay, let X be a complex manifold. The Calabi-Yau complex is a sheaf of vertex algebras on X introduced by Manifolds, Shigman, and Venture in 1998. The sheaf is bi-graded by Fermion number P and conformal with K. So with 0 P's coincide with ordinary de Rham sheaf. So this sheaf can be regarded as a vertex algebra version of de Rham sheaf. Now its greater dimension of its cohomology is electrogenous. And if X is a Calabi-Yau manifold, its cohomology can be identified with the infinite volume limit of the half-twisted sigma model. Now, about the global section of this sheaf, there's only a few known examples other than affine space or torus. Of course, affine space or torus. For affine space, it's trivial, and torus is just almost a trivial thing. I think just 2 years, 1 or 2 years ago, for any conclusive group G of SL2R, Xuanzong Dai construct a base of G invariant global sections of the Calabi-Yau complex on the upper half plane, which are holomorphic at the cusps. So this can be regarded as a global section of the Calabi-Yau complex on the modular curves. In fact, for any modular form, you can construct a family of global sections. We have the following result before. If X is a K3 surface, the space of global section of the Calabi-Yau complex of X is the simple and equal 4 superconformal vertex algebra with central charge C equals 6. So, in fact, use this result with Calabi-Yau duality theorem. We can decompose the decompose the algebraic of K3 surface into the character of an equal 4 superconformal vertex algebra. Okay, now let's construct the Calabi-Yau complex. Let V be a d-dimensional complex vector space, and then x1 to xd be a base of V, and x1 prime to xd prime be still base. Let WV be the.
Can I interrupt for a minute? Can you go back to your K3 results?
This one?
Yeah. So what is the central charge of this N equals 4 algebra?
Central charge is C equals 6.
Okay. Is that easy to see? Why 6?
Why 6?
I would have expected 4, but Why is it 6?
It is equal to 3D. D is dimension. So K3 is a 2 dimension, always 3D.
Okay, got it. All right, thank you.
Okay. Okay. WVB is the tensor product of the D copy of beta gamma BC system. So it has 2D even generators, beta and gamma, and 2D odd generators, B's and C's. Their non-trivial OPs are the following. So these are just I think a free field. Now let U and U gamma be a complex coordinate system of a D-dimensional complex manifold. Now let OU be the space of holomorphic functions on U. So it has the OU will have C gamma 1 to gamma D model structure just by identifying the action of negative modes gamma with the product of the gamma I, called gamma I. So OU will be this model structure. Then the space of section on U is the localization of WV on U. It's the tensor product of beta gamma BC system with the holomorphic function on U. Of course, previously this is just the space, just localized as a vector space. As a vertex algebra, this is the space of section on U is the vertex is generated by the beta and B and C. This is just the previous beta B C, and then the function F on the holomorphic function on U. These generators will satisfy the following OPs. The beta with the function F just is the following. So the zero modes of beta on F is just take a derivative of F, and the BC is set, as well as the normally ordered relations. The weak product of FG, just the function product of F with G. Now, if we change the coordinate, it to the gamma D be another set of coordinate on U, with F and G is the transition function, then the coordinate transformation equation for the generators of this sheaf are the following. Here you can see that the D gamma and the C is change like different forms, and the B change like vector field. The only difficult part is complicated part is the betas. The cohomology of this sheaf is called Calabi-Yau cohomology of X. Now this sheaf has a soft resolution. I use the sigma X CH star. Locally, this sheaf can be realized that the beta gamma BC system tensor with the space of anti-holomorphic forms. This is complex anti-holomorphic forms, so this will become a complex. So now the Calabi-Yau cohomology equal to the cohomology of the complex of this complex, the omega X CH star, the global section on here, the smallest global section. With the D bar, with differential operator D bar. Okay, now the space of global section of this sheaf will be the kernel of D bar in degree 0 part. Now to describe the global section on compact Calabi-Yau manifold, let me introduce some subalgebra of the beta gamma BC system. Let the W plus V be the subalgebra of WV, the beta gamma BC system, now which is generated by the beta, B, C, and D gamma. So W plus V just the there's only no element is gamma, or there's other stuff is or other stuff in WV are all in W plus V. Now let Q be the Q and L, J, G be the following. So this field will generate the n equal to superconformal algebra with central charge C equals 3D. Now here the central charge is given by the velocity law L minus 1/2 dj. Of course, L is L itself is velocity law, but when we calculate the central charge, we use this one, L minus 1/2 dj. Why use this element? Maybe we can see the following. Maybe I think we can see later. Okay, now let A0 be the vertex algebra generated by the previous n equal to algebra and the following 4 elements. Essentially, there are 2 elements. E is corresponding to the volume form, D is the dual of E, and then the other 2 elements, B, C, is generated by this 6th element. Q0 mode on B and G0 mode on G. I write down this 8 element because A0V will be strongly generated by this 8 element. If D is even, let A1V be the vertex algebra generated by the field QLJG and the following 4 elements, D prime, E prime, B prime, C prime. CSM here, E prime will corresponding to the symplectic form, and the D prime is the dual of the E prime. And then the other 2 elements are generated by Q0 mode on act on D and G0 act on E. CSM, this A1V was strongly generated by this 8 element. Here A sub 1V is an n equal 4 superconformal vertex algebra of central charge C equals 3D. This W plus V has a positive definite form with the following property. Here you can see that the n modes of beta, the dual of n modes of beta is the negative n modes of D gamma, and the dual of n modes of B is negative n minus 1 modes of C. Use this one, we immediately have the following. The dual of Q, the dual operator of Q will be G, the dual operator of J will be J, and all the same. Here in particular, the dual operator of L is L minus n minus 1J and then n minus this one. And here, this L will be not self-dual, but if you let L minus 1/2 of dj, then the velocity law will be self-dual. So when we calculate the central charge, use this L expected. Whatever, W plus V will be a unitary dependency of A0V and A1V. And in particular, you can see that these 2 vertex algebra are simple. Now, on general complex manifolds, LG are globally defined. But J and Q are not globally defined, but their 0 modes are globally defined. On Calabi-Yau manifolds, I mean that the least flat manifolds, complex manifolds, L, G, Q, G are globally defined. And furthermore, if X has a holomorphic volume form, then D, E, B, C are globally defined. So A sub 0, V are globally defined. If X has a holomorphic symplectic 2 form, then D prime, E prime, B prime, C prime are globally defined. So A sub 1, V are globally defined. But as all of them are all of the global element, this is our theorem. If X is a d-dimensional closed Kähler manifold with holonomic group G is a special linear group, special unitary group, then the global selection will be just is sub 0 V. If X is a d-dimensional closed Kähler manifold with holonomic group G is a symplectic group, then the global selection is A sub 1V. In the first case, we have a holomorphic volume form, and the second case, we have a holomorphic symplectic form. Okay, now the previous is special case for general least flat Kähler manifold. X will have a finite normal cover. The following here, T2L is a flat Kähler torus, and Xi closed manifold with dimension di, and its holonomic group with SUDI. Now Yj is a closed manifold of dimension 2Lj with the holonomic group is SPLJ. Then immediately we get the following corollary. If G is the covariant transforming group, then global selection of X is the global selection of the covariant space, G invariant part of the global selection of the covariant space. And by previous special case, we can found the global selection of the covariant space. So we immediately get the covariant space as the global selection on X. Here, W plus CL is the global selection of on the flat Kähler torus, and A sub 0 is on Xi, and A1, A sub 1 is on YJs. Now, to show this theorem, we roughly speaking, there'll be two steps, and the middle part will be will be on the algebraic vector field on V. Let's see what's this one. The algebraic vector field on V just the vector field on V, and with the here with V and look like this one. And if x1 to xd is a base, and x plus 1 is still base, then degree n part will be look like this way. Will be polynomial, and the partial part b part. Now let omega 0 be the volume form, and if d even let omega 1 be the symplectic form, then let vector v omega I be the space of vector field which kill omega I. This is Lie algebra. In fact, it's a simple Lie algebra. It is called Lie algebra Cartan type. Vector v omega 0 is called special series, and the vector v omega 1 is called Hamiltonian series. This Lie algebra is a graded Lie algebra. Degree negative 1 part just asymptotic to V, and degree 0 part is just the classical Lie algebra. Same thing.
Hi, Bailin. Sorry for interrupting you. So there is a question in Q&A. So are there cohomology groups of the Chiral de Rham complex?
Yeah, as a sheaf.
As a sheaf, so sheaf cohomology sheaf.
Sheaf cohomology. Sheaf cohomology.
Sheaf cohomology. Okay.
Sheaf cohomology, not as a complex, not as a complex. Because as a complex, it's trivial, just the ordinary cohomology. And regard the Chiral de Rham complex as a sheaf, then calculate its sheaf cohomology.
Okay, thank you.
Okay, now the vector zero part is the classical algebra. And then degree I part of the algebra is irreducible representation of degree zero part. So whatever the vector, this algebra are generated by we can generate by degree -1 and degree 0 part and an element of high degree. Now, there the canonical action. This vector, the algebraic vector field can act on the beta gamma BC system. The action is given by following: give vector field, you take this operator to get 0. This is the Q0 mode of PIBX. Here you replace xi by gamma xi and replace this vector by bxi. Then you take the Q0 mode. The total space and the total element take the 0 mode act on the beta gamma BC system. This is the algebra morphism of the algebra. Now, the special series and Hamiltonian series as a subalgebra of algebra will act on beta gamma BC system slow L. Now we have the following theorem: the invariant space of this Hamiltonian series and the special series on beta gamma BC system is just equal this AIV. And the first equation is easy because this is partial over partial xi in the algebra, and then this means that the invariant part will Q by beta, and there will be no gamma, so just will be W plus V. And also it is easy check that A sub IV, this algebra is vector V omega I invariant. The difficult part is to show that this in fact is equal. We need the following construction. Let S sub 0 be the set of beta d gamma b c, negative mode of them, negative mode, only negative mode. So these operators are super commutative. And now let SWV be the algebra generated by them. There is a canonical isomorphism from SWV to W plus V, just act on the 1, because this negative modes act on 1. This pi will commute with the derivation of the D. This D is in the vertex algebra element. The velocity act the 0 mode of V of the velocity. Now we have the following grading of SWV. Here, the grading is given by the element of gamma has degree 2, the element of C has degree 1, and the element of beta and B it has degree 0. Then we give the polynomial degree of this element. And let GI be the vector V, vector 0 V omega I, and the classical algebra, the classical spatial linear and the spherical linear. We consider its local algebra. Now, there is the local algebra, GIT, will act on this SWV. The action is given by following. Just G act on Xi, and N will increase the modes. Now, we have the following lemma, the last lemma. The GIT invariant of SWV is generated by the inverse of eight element. Here the pi is the isomorphism. So SWV, the GIT invariant of SWV is generated by the inverse of pi of eight element. This lemma is because we have we have the following theorem. We have the theorem and for G of SOD or is a special linear group or the special linear or symplectic group, then the arc space of this the following arc space is I think it's how to say the arc space invariant of this one. This map is surjective. This map is surjective. So this will imply that the SWV GIT invariant is generated by negative modes of beta, gamma, B, C. G invariant of negative modes of this one. But by classical invariant theorem, this space is just generated by the eight element of the eight elements. So we have this lemma. Now, the action of GIT on SWV will preserve the gradient of SW. So for any A in W plus V, take inverse of pi. Since SW is graded, you can write as AK plus AK minus 1, something like this, with AN is in SWN. The interesting thing is that the leading term of AK, the leading term is GIT invariant. If A is sorry, I think if A is GIT invariant, I think I missed something. If A is GIT invariant, then AK. Sorry. If A is if A is invariant under special linear group, special series or Hamiltonian series, then AK is GIT invariant. So AK is GIT invariant. So by previous lemma, then AK can be like this way, just a polynomial representation. So let B the corresponding normal order polynomial of SI. Now inverse of B by pi will be BK plus BK minus 1, like this way. And particularly BK will be AK because they are similar. AK, we consider B like use the A form of AK, this will be same. So inverse of pi inverse of A minus B will look like this way. And since B is vector V omega I invariant, so the space will be vector V invariant. So by induction on K, we can conclude that this equation is true. Okay, now previous theorem was the following theorem. We also have the following theorem. If X is a d-dimensional compact Kähler manifold with the holonomic group G equals SUD, and W0 is a Novel-Vanish holomorphic deform, then the global section is isomorphic to this invariant space. That means the invariant of the beta gamma BC system under the action of Hamiltonian series. If X is a d-dimensional compact Kähler manifold with holonomic group is a symplectic group, then there will be a holomorphic symplectic form. Now let W1 be holomorphic symplectic form, then H0, then the global section will be beta gamma will be the invariant in beta gamma system acted by the Hamiltonian series. this theorem with previous theorem, then we get the our main theorem, the global section equals A0 and A1. Previously I have given. So the last part is that we should prove this theorem. So here I will give a sketch of the proof. First, let's look at the soft resolution of the Chiral de Rham complex. Locally, this soft resolution, the complex of soft resolution of Chiral de Rham complex locally will be locally on U. Now let Hij be the Kähler form, and we consider the following 4 elements. The both gamma I is just the Ij with the gamma I and similar something like this. Now these 4 elements, these elements have non-trivial OP just like this one. This is the same as the beta d gamma. Just here both B is just like beta and the gamma just like, and here the gamma is like a gamma and then BC is similar. Both B's is similar. So they will generate a vertex algebra which is isomorphic to W plus V. And this operator commutes with anti-holomorphic functions. Now, if U theta and gamma theta is another holomorphic coordinate system of X, then the change of coordinate formula will look like this way. Here you can see that gamma change like gamma and C change like differential form, and B and beta change like vector field. The good thing is that under change of coordinate, the transition function are anti-holomorphic. Anti-holomorphic function is commute with action of this element. So we let SWT be the bundle of the super commutative algebra on X with the fiber at X is the polynomial algebra of this one. And then this bundle is isomorphic to the following bundle, which is used to calculate the algebraic. Now we can have this map from the vector bundle, to the soft resolution of Chiral de Rham complex. The map will given by following. Just act on A to F. Now, this IU is an isomorphism. It's obviously it's isomorphism, and it is compatible with the change of coordinate. It's compatible with change of coordinate because when we change a coordinate, the change function is anti-holomorphic. So it has nothing to do with the VOA structure because they all commute with the VOA element. So we get an isomorphism of this sheaf. Now we can calculate the cohomology of the cohomology of Chiral de Rham complex. Use this complex. It's defined by vector bundle. The only thing we changed is that the d-bar operator, when we pull back the d-bar operator, it will become like this one. It will become d-bar plus f. Now, we we solve the problem of vertex algebra because vertex algebra is complicated when we change coordinate. After we solve the vertex algebra problem, then the difficult part becomes f. The f is quite complicated. It look like this way. So it's quite complicated. And here gamma is like this way, and then here we calculate that. And here the theta is S-1 covariant derivative of the curvature. Here you can see that the left part for every factor, the left part is involve vertex algebra, and the right part is involve geometry of x, the curvature covariant of x. So we have divided it in two parts. You use this formula, we can calculate that the dual of d bar, if x is flat, then for n smallest section, the dual of beta commutative with f. With this property, then an element killed by d bar plus f is the same as it's killed by d bar and both killed by d bar and killed by f. Now, on compact manifold, on this flat compact manifold, the global section killed by d bar is easy to calculate because it's this flat and this is a vector bundle. So just the space of a holomorphic section on this bundle. Since it's a holomorphic section, it's a rich flat manifold. So the holomorphic section just the horizontal section. So it will equal to the G invariant on the fiber. So totally, when we try to calculate the global section of de Rham complex, then we calculate the element killed by d bar plus f, and the same as that G element in the fiber and killed by f. And this is the same as beta gamma BC system invariant on beta gamma BC system acted by the spatial series or Hamiltonian series. So we show this theorem at last. Okay, I think I finished here. Thank you.